Welcome to our first science series for the school year. Very pleased to have with us tonight Dr. Robert Piccioni, all the way from California, Los Angeles, so we were training very bad traffic stories. Got his degree in high energy physics from Caltech, and for any physics people out here, he knew Richard Feynman. Very cool. He has numerous patents in medical devices, microelectronics, and smart energy. After he retired, he started to develop an interest in popularizing science. He's written 2 books, he teaches, and sounds like you're busier now than you were when you were lecturing as an instructor. So he's going to talk to us tonight about the life and discoveries of Albert Einstein. So would you please welcome Robert Piccioni.
Thank you very much. It's a great pleasure to be here. Can you hear me? Is the sound system doing its job? Yeah. Those in the back row? Great. This is going to be fun. Even if you fear physics and are allergic to math, this is going to be enjoyable and entertaining. And I'm trying to make the point that everyone who can change money can understand Einstein. So there's going to be no complex stuff tonight, just enjoyment. I guess we need to turn down some lights. Albert Einstein is, without a doubt, the most famous scientist in history. He was chosen by Time magazine as the most important person of the 20th century. And you think about how many people lived in the 20th century and all the amazing things that happened. It's really incredible to have chosen Einstein, a physicist, as the most important person of the century. And Time magazine said of him that he had the greatest mind and was the paramount icon of our age. And in fact, his name has now become synonymous with the word genius. So one might think that Einstein's life was a bed of roses, an endless sequence of accomplishments and accolades. But actually, the truth is very much different. Hardly anyone has failed more often than Albert Einstein. Hardly anyone has faced more rejection in their life than Albert Einstein. He got off to a bad start. He was very slow to learn to talk and earned the nickname Dopey. His younger sister had to help him communicate. He was expelled from the 2nd grade for being inattentive, daydreaming, if you will, and he dropped out of high school with 2.5 years left. He tried to get into a lower level college, but failed the entrance exam. Had to reapply the next year. He did well in college initially, but he started skipping classes that he found boring. He didn't do assignments he thought were beneath his intellectual dignity. And pretty soon he ended up graduating with the 2nd worst grades in the class. And along the way he had made a point of publicly insulting his professors, and so they considered him, yes, bright, but terribly insolent, and his math professor called him a lazy dog. So with horrendous references and very poor grades, Einstein was the only member of his graduating class who couldn't get a job. He applied for every position at every technical institute and university from Norway to Italy, and for years he wasn't even granted a single interview. He was summarily rejected at every opportunity. Had it not been for the fact that he had wealthy relatives who gave him a regular handout, this man would have been living on the streets. Finally, after 2 years, the father of one of his friends who had a lot of juice in the Swiss government, managed to get a position opened in the patent office with Einstein's credentials in mind. Or I should say, with Einstein's lack of credentials in mind. So Einstein figured this was a setup, a slam dunk. All he had to do was show up. He went to the interview confidently and failed the interview. He was rated technically unqualified to be a clerk. Fortunately for science, The search for civil service competency was trumped by political influence, and Einstein was hired nonetheless, even though he was technically unqualified. Now, of course, that sort of thing would never happen in our society today, but that's the way it was then. Hoping that he would get a raise, he tried to get a PhD, applying at the University of Zurich, and in his PhD thesis, he publicly criticized by name several of the most prominent physicists of the day, and lo and behold, his thesis was rejected. So this young man had firmly placed himself on a road to failure and obscurity, and it seemed that he would fulfill the prophecies of his many detractors and never amount to anything. But Einstein had one characteristic above all others, which I think is the most important ingredient to success in any field, and that is he never gave up. Einstein had a tenacity, a perseverance that was truly unmatched. He could work on a problem virtually night and day for 10 years, if that's what it took to solve the problem. He just never gave up. And that's particularly amazing in our day and age, when it seems that many people, for those many people, instant gratification doesn't seem to come soon enough. Asked later in life why he had been able to solve these problems and other people hadn't, he said that it's not that I'm so smart, but that I stay with problems longer. Meaning he never quit. This picture that you see here shows you the entire contents of Einstein's lab. The most famous scientist in history only used a pad of paper and a pen. He never did an experiment. He never made an observation. He never made a measurement. Everything that Einstein discovered came completely out of his own brain. Truly incredible. And in 1905, things that he'd been working on for as long as 10 years finally came to fruition, and he was able to publish 5 spectacular papers that revolutionized all of physics. This is called Einstein's miracle year, and no one in science has ever come close to matching this sort of achievement. Any one of these papers, in my opinion, could have won a Nobel Prize. Any one of these papers by themselves would have been the crowning achievement of any scientist's career, and Einstein published 5 of them. And they call it the miracle year, but that's a bit of a misnomer because he did it all in 7 months. Could have taken the rest of the year off. He solved all the open problems in physics of the day, and he told scientists that they didn't understand how to measure weight, distance, or time, and that they really didn't appreciate the true nature of light, or matter, or motion, or space, or time. So if you take all those things out of physics, there isn't a whole lot left. Basically, he tore out the whole foundation of physics and replaced it with a whole new set of theories. So, naturally, one might think that having revolutionized all of science, universities throughout Europe would be beating a path to this man's door with these glorious job offers, and all he would have to do is pick the best one and live out the rest of his life in comfort. So he waited, and he waited, and he waited, and nothing happened. No one responded to his papers, with dead silence. And years went by. Finally, at the end of 1905, for the least revolutionary of all these 5 papers, he was granted his PhD. And 2 years later, in frustration, still not having a job offer, he applied to be a high school physics teacher and was rejected because he was obviously unqualified. Didn't even get granted an interview. Finally, 4 years after his so-called miracle year, it had been a miracle for science, but not for Einstein yet, he got his first academic appointment as a junior professor at the University of Zurich. He is now 30 years old. He has failed at everything, at every turn, throughout his entire life until the age of 30. He was in the patent office for 7 years, And this is a guy who easily could have quit anywhere along the way, but he never did. And he finally got his first small measure of success at the age of 30. He then climbed the academic ladder, and within 4 years, the leading physicist of the day, Max Planck, said of Einstein that there was hardly a major problem in physics to which Einstein had not made a remarkable contribution. And based primarily on Planck's enthusiastic support, Einstein was granted the greatest job imaginable, not just for a scientist, but for almost anyone. The job came in 3 parts. He was appointed immediately a full professor of physics at the University of Berlin, the most prestigious institution in physics in the world, with the promise that he would never have to teach a single class. He was appointed to a directorship of a new institute of physics with the promise he would never have to do any administrative work whatsoever. And thirdly, he became a member of the Prussian Academy of Science with the promise he would have no duties there either. And all 3 of these came with a full salary. So here's your office, here's 3 paychecks. You don't have to do anything, just sit and think. You come up with something nice, let us know. That's a job, right? I want that one. And finally, he received later the highest honor in physics, which is the 1921 Physics Nobel Prize. So let's talk about what this man discovered and how it impacts all of our lives today. Einstein was the one who found the first definitive proof that atoms existed. Now we all know that atoms are what everything around us is made of, and it's easy to think that that notion has been around forever, but actually before Einstein, physicists were moving away from that idea and replacing it with other ideas. And the debate about the existence of atoms or not, whether matter was made of these small particles that were all linked together, or whether matter was ultimately just smooth like water, that debate was the longest running debate in the history of science. It lasted 25 centuries. And it was Einstein who was the first to put an end to that debate by defining a mechanism for testing the theory to see whether atoms existed or not. Nowadays, with our most advanced microscopes, we can actually image individual atoms. These are xenon atoms on a nickel surface, which have been imaged by an atomic force microscope in the central research labs of some big corporation or another. The next is Einstein solved a mystery called the photoelectric effect, which allowed people to design better and better photosensing devices, ultimately leading to the charge-coupled device, which is the sensing element in every digital camera, every video camera, and is now used in all telescopes, including the Hubble Space Telescope, which is shown here. Einstein also developed a theory for lasers. Lasers read our DVDs and CDs. Lasers sculpt our cornea. Lasers carry our communications across for the internet and telephone across fiber optic cables around the world. And lasers are the basis of countless medical, industrial, and military devices. And they're good for pointing at slides also. Einstein also developed 2 theories of relativity, special and general theory, which are essential to the proper functioning of the global positioning system, the GPS. So the device that gets you where you want to go depends in its entirety on a man who couldn't find his own keys. Without Einstein, if you got home on Monday night, you'd be 6 miles off on Tuesday, so you'd be in a different city, and by the end of the week, you'd be out in the ocean. So the GPS would really be worthless without Einstein's theories. Einstein was also one of the major contributors to the theory of quantum mechanics, which resulted in solid-state physics, microelectronics, and led to all of the digital widgets that we have in our society today, computers, iPods, iPads, this, that, and the other. And Einstein's most famous equation, E equals mc squared, that we'll talk about in more detail in a minute, led to the development of nuclear weapons, which ended the Second World War, the development of nuclear power, and will lead us in the future to even smarter energy that is going to satisfy our needs while preserving our environment. But no one's perfect. Einstein did not bat 1,000. He might have only batted 500. That's nonetheless outstanding for a baseball player and equally outstanding for a theoretical physicist. So, as anyone would reasonably agree, Einstein was the world MVP, which of course means the most valuable physicist. Okay, let's talk about this famous equation, the most famous equation in all of science. Now, I think everybody has seen this equation, E equals mc squared, on a coffee mug or a t-shirt, or God forbid, maybe even a physics book. I think we've all seen it. But how many of us would be comfortable explaining it to our kids? Maybe a lot less. But I claim that if you can change money, you already know what this equation means in that different context, in the context of money. And let me show you why. Before Einstein, physicists knew that there were many different forms of energy, and we could convert energy from one form into another. So, energy came in the form of heat, gravitational potential energy, a rock at the top of the cliff, chemical energy, that's what gasoline has, and we can convert that chemical potential energy into the kinetic energy, the motion energy of race cars. So this is what physicists knew before Einstein. Einstein came along and said something very remarkable. He said, mass is another form of energy. Even though mass looks nothing like heat and work and gravitational potential energy or anything else, all of which are very intangible, mass is completely tangible. Even though they look so different, Einstein said that they're really the same. That mass is just another form of energy. So this object that I hold in my hand, and indeed my hand itself, are really compressed forms of energy. In fact, a compressed form of a fabulous amount of energy. And he said we can convert mass into energy, and we can convert other forms of energy into mass in accordance with this equation. And this, I claim, is very much like changing money. So we know money comes in many different forms. There's dollars and euros and pesos and yen, and we know we can convert from one to the other. So if you were to get on an airplane and go to Tokyo, you would need to convert a very large number of dollars into yen, because Tokyo is a very expensive place. And it's easy to do. You take the number of dollars that you have to convert, you multiply by some exchange rate, and that tells you how many yen you're going to get. Right? Not so tough. Well, Einstein said the same thing here about mass and energy. He said if you want to convert a certain amount of mass into a different form of energy, like heat, you take the amount of mass N, multiply by the exchange rate, c squared, and that'll tell you how much energy you're going to get in this other form. Right? C squared is the exchange rate. That's all there is to it. Mass and energy are the same. You can change one for the other. C squared is the exchange rate. C is the speed of light through empty space. It's the fastest that anything can possibly travel. It's a very big number. It's 671 million miles per hour. Big number. C squared is C times C, so that is a very big number. So Einstein is saying that even a very small amount of mass times this stupendous exchange rate will produce an awful lot of energy. So just how much? Well, if we were to take all the mass energy in a U.S. penny, one single U.S. penny, using Al's equation, we would be able to convert that into useful work energy that would supply all the needs of 1 million people for a day. 1 million people for 1 penny for a day. Or equivalently, this penny has as much mass energy as we now get by burning 2 million gallons of gasoline. So perhaps the intrinsic value of gasoline is 2 million gallons for a penny. I hope none of you is getting ripped off at the pump. Now this is such an important equation that I'm happy to tell you I just happen to have an image of the moment that Einstein made this great discovery. It's a very historic picture. You see that he decided that mass was equivalent to energy, and all he needed now was the exchange rate. So he simply had to go through the alphabet and find the equation that fit just right. And if any of you guys turn that in tomorrow for your extra credit, you're not going to get it. Okay, let's take Einstein's idea. What Einstein told us about energy, which is all of it comes from mass, and let's use that idea to attack a practical problem. How is our society going to get the energy it needs without destroying the planet? Right? You hear about global warming, greenhouse gases, on and on. What are we going to do about it? Well, it's a big problem, yes. But human beings are problem solvers. That's what has propelled us to the top of the food chain. We're spectacular problem solvers. So what are we going to do about it? We're going to figure out what the options are and do the best thing, right? That's what we do so well. Well, it turns out that all of us together in a recent year consumed a total amount of energy in all the different forms that we use it, which is equivalent to 25 trillion kilowatt hours. And that turns out to be as much energy as you would get if you took 1 ton of mass and converted it into energy according to Einstein. 1 ton of mass. So our problem really is, how is our society going to convert 1 ton of mass every year into energy in the best possible way? What are the options? Well, we can burn coal. We've got a lot of coal, makes a lot of heat. What if we wanted to get all of our energy from coal? It turns out we need to burn 5 billion tons of coal, and if we weighed everything carefully beforehand and everything carefully afterwards, we'd find that 1 ton was converted into energy. The total mass afterwards would be 1 ton less than it was before. So we have converted 1 of the 5 billion tons into energy, and we have converted all the rest into pollution. Right? Would you knowingly do that? This is like running a business in which you have to make a sales call on every human being on the planet to get 1 order. Right? Terribly inefficient. Not what any reasonable person would do. But this is where we get a vast amount of our energy. It's obviously a very dirty process. Well, what's better? We can burn gasoline. Gasoline has more pop per pound than coal. Turns out we only need to burn 2 billion gallons, 2 billion tons of gasoline to get our 1 ton of energy, and we're left with 2 billion minus 1 tons of pollution. And we know that what comes out of the tailpipe isn't clean either. So this is a little better, but not great. Well, why is it with all the clever scientists and engineers in the world, we can't do a whole lot better? Why can't we do, for instance, 3 times better? If we could do 3 times better, energy would cost 3 times less, there'd be 3 times less pollution, everybody would love it, right? So why don't we just do it? Well, we can't. And the reason we can't is because of the fundamental properties of atoms. Energy comes from atoms. Atoms are very simple things. They're very small and very simple. They just have 2 parts, the inside and the outside. The inside is the nucleus. It has a positive electrical charge. The outside is a cloud of electrons with a negative electrical charge. And at least as far as electricity is concerned, opposites really do attract, and that's what keeps atoms together. And my drawing is not to scale because the electron cloud is really 100,000 times bigger than the nucleus. So if you enlarged an atom so that the nucleus was the size of a golf ball, the electron cloud would be 2 miles across. It's vast. But all the mass is in the nucleus. Even though the nucleus is so small compared to the electrons, it has 4,000 times more mass on average than the electron, and millions of times more energy than the electrons. The nucleus is all about what the atom is. The electrons are around for the ride. And when we burn coal, gasoline, or even this reaction, which is powerful enough to send rockets to outer space, converting hydrogen and oxygen into water, what we're doing is we're rearranging the electrons. We're playing with the parts of the atom that have almost no energy. Right? The nuclei are completely unchanged by any chemical reaction, and it's the nuclei where the energy is. So as long as we're playing with the electrons, we're going to be immensely inefficient. We're going to get 1/1000th of the mass of the fuel converted into energy, and all the rest is going to be pollution. We're stuck with that as long as we play with the electrons. If we want to get a lot more energy out, we have to go to where the energy is. The energy is in the nucleus. And there's two ways to get energy out of a nucleus. You can make it bigger, or you can make it smaller. I bet some of you thought nuclear physics was complicated. Let's talk about the two. If you take a very large atom like uranium, and you allow it to split or cause it to split, it'll split into two still very large atoms, and you will get out about 100,000 times as much energy as a typical chemical reaction. That's the good news. Bad news is, these are highly radioactive waste products. If we were to get all of our energy from nuclear fission, we would need to burn 50,000 tons of uranium-235 every year. We would get our 1 ton of energy. We'd have 49,999 tons of radioactive waste. We had that problem solved. We were going to bury it all in Harry Reid's home state until he became the head of the Senate. And that was out. So that's a problem. The other alternative is called nuclear fusion. This is really the opposite. We're taking small nuclei, we're merging them together to make a bigger nucleus, and the end products of nuclear fusion include carbon, oxygen, nitrogen, iron. All the elements from which life is made. These are not radioactive waste. These are vital elements. This is where all of the carbon in the universe came from, this process, nuclear fusion. This is how nature makes energy. Nature does not pollute. Nature is not inefficient. This process is 10 million times more efficient than burning coal, and it's pollution-free. This is what nature does. So, in the center of every star, this is a picture of our sun on what might be called a bad hair day. That white dot shows you how big the Earth would be if it was in the same image. Fortunately, we're never that close to the sun. In the center of stars like our sun, and even larger stars, these elements of life are created by the process of nuclear fusion. When the universe began, there wasn't a single atom of carbon or oxygen in the entire universe. Every single atom of carbon and oxygen and all these other heavy elements that are essential to life were created in a star. At temperatures of hundreds of millions and billions of degrees, 90% of the atoms in your body came from a star. And when those stars died and exploded and spread their contents throughout the cosmos, the gas clouds in our galaxy were seeded with these vital elements. And that's where we come from. We are the children of the stars. We are born with stars inside us. If we were to be able to do what the stars do, which is hydrogen fusion, we would need to burn only 133 tons of hydrogen every year to get our 1 ton of energy, and the byproduct would be helium gas, which is a perfectly clean substance. So if we master that, we will have a process that's 40 million times more efficient than burning coal and is pollution-free. Physicists have been working on this for 50 years. This is no new news. But what is new news is that the difficult process of merging charged nuclei together can now be sidestepped. There is a new discovery that's been made, putting together known physics that will enable us to produce fusion-level energy in very simple, small reactors without radiation and without extreme temperatures and pressures. And I believe that within 3 or 5 years, we're going to have a demonstrated capability to produce energy at phenomenally more efficient levels with virtually no pollution. And that will change the face of mankind. That will provide the people in Africa with water. That will, eliminate global warming. It's going to change virtually everything about geopolitics and society and make it much better. But it's still not as good as the best. The best is to get 100% efficiency And that we could do by taking our penny and launching it into a black hole in just the right way. So if we manage to get our hands on a black hole, not quite literally, and it was the right type of black hole, spinning very rapidly, and we launched material into the black hole, 100% of the mass of that material can be converted into useful work energy. 100% efficiency. The trash, or whatever you launch into the black hole, will be consumed into the black hole. Not a single atom will ever return to our universe again. So it is a 100% clean process, and it's 100% efficient. Not too bad. We have to look forward to that. Okay, let's talk about relativity. Einstein's theory of special relativity replaces Newton's laws of motion. The key principle that Einstein proposed was that the speed of light will always be measured to have exactly the same value, no matter who's measuring it or how. And that value is this quantity that we talked about before, named c, 671 million miles per hour. So imagine that we have a jet plane moving very rapidly with a laser shooting out the front. From the point of view of the crew, the laser is moving away from the jet at the speed of light. It is light. The question is, how fast is the laser beam moving relative to the air or to the ground, relative to us who are sitting still? Well, if this is a very fast jet, the new Air Force model that your tax dollars have developed, moving at 330 million miles per hour, half the speed of light, then it's tempting to say 1c, the speed of the laser beam, and add it to the speed of the jet, a half c, and end up with 1.5. Right? If you were swimming in a river and the river was moving at 5 miles an hour and you're swimming at 2.5 miles an hour, you're moving relative to the bank at 7.5 miles an hour. You just add the two, right? Well, then you get 1.5. And Einstein said, no, it's always c. Einstein said 1 plus a half is 1. You can see why it took years for people to believe it. He said you can't just add them, you have to use a more complicated equation. And that complicated equation arises because measurements are relative. Einstein said that the laws of physics are universal, but different people under different circumstances will measure certain quantities to have different values. They will measure lengths to be different, they will measure times to be different, and they will measure weight to be different in a very specific way. Let's talk about time. That's the easiest to understand and perhaps the most interesting. Newton said that time was an absolute and universal quantity, which meant that clocks everywhere throughout the universe would run at the same rate. Time always evolves at the same rate, independent of everything else. And Einstein said none of those things are true. That time is relative. It depends on who's measuring, how fast they're moving, what position they are in a gravitational field. And in fact, Einstein said no two clocks in the universe will keep the same time. So this is why. Imagine the simplest possible clock, a clock that has no moving parts. Einstein said that simple clock would consist of two perfect mirrors with a photon that's bouncing up and down. And as the photon hits each mirror, you count tick, tock. Very exciting, right? Tick, oops, tock. Okay. Now, imagine that you have two of these guys, two identical clocks. And we put one of them in a jet plane moving at half the speed of light, and it shoots off to the right. Okay, so what's going to happen? Well, the mirrors are going to go to the right along with the jet, and the photon is going to go to the right along with the jet. And we see here that to get from the top mirror to the bottom, this photon has to travel down the diagonal, which is long. Whereas the same clock on Earth is traveling on a shorter distance. So it's going to take longer for the photon to move down the diagonal than it is for the photon in the stationary clock to move vertically up and down. And this is because these two photons all are moving at the same velocity, always moving at the speed of light. This one can't move faster and it can't move slower because it's a particle of light, it has to move always at the same speed. But since it has a longer distance, it's going to take more time. So while the particle on the left goes tick-tock, the particle on the right has yet to go tick. It's running about 40% of the rate of the other clock. Time is slower in the jet than it is on the ground. Does this mean the crew ought to buy a better clock? No. Everything in the jet will proceed at a slower rate. The crew's heart will beat slower. Their brain waves will rate slower. Their fingernails will grow slower. Everything in the jet will go slower by exactly the same amount. The amount dictated by the perfect clock. And if the jet crew looks back at Earth, they will see exactly the same thing with us. They'll say, my clock is fine, thank you very much. The photon's going straight up and down here in the cockpit of the jet. And it's your mirrors that are moving along with the Earth. And it's your photon that's got the longer path length. And it's your clock that's slower. And both of these are true. To us, the crew's clock looks slower. To the crew, our clock looks slower. And it took the genius of Einstein to figure out how all of this could be simultaneously true. Einstein's other theory of relativity is called general relativity, and this is specifically aimed at gravity, so it replaces Newton's theory of gravity. Newton said that gravity is a characteristic of mass, and only mass. It was only mass that produced gravity, and only mass that responded to gravity. His equations exactly predicted the orbits of planets around the sun, the moon around the earth, the falling of apples from trees, and all these things, but Newton had no explanation whatsoever as to how it really worked. He couldn't say how the sun could reach out across 93 million miles of seemingly empty space and grab onto the earth and pull it. He knew it did, but he couldn't explain why. His equations worked, so people just sort of forgot about that for 250 years and claimed it was due to something we don't understand, and we'll call it action at a distance. Einstein said none of this is true. Einstein said it's not just mass, but all forms of energy that cause this effect we call gravity, and that gravity, in fact, is not a force at all. There is no force between the sun and the earth. There is no force between the earth and the apple. Things move in peculiar ways, perhaps, because they're moving through space which is curved, unlike what Euclid taught us about. And he said, all forms of energy, not just those that have mass, will cause this curvature. So if you think about space just being two-dimensional for a moment, since I can't draw a picture beyond that, if you think about space being a bed sheet, and you were to lay a bowling ball in the middle of the bed, then this is what you might imagine would happen to the bed sheet. It would be depressed under the bowling ball, and it would stretch. It would stretch all the way out to the edge of the sheet, however long that is. And this is what Einstein says happens to our space. The sun depresses the bed sheet, and the earth is rolling around in this depression like, an olive running around in a salad bowl. And the reason the earth is orbiting is because it's moving through this curved space. Sounds all very complicated, but actually we have something that we're more familiar with that does the same thing. So this piece of apparatus from a child's playground is also curved. And anything that enters at the top, in order to get to the bottom, has to go around and round, because the space has that shape. Doesn't matter how heavy, doesn't matter how fast, it has to go round and round because the shape is curved. So in exactly the same way, but in many more dimensions than I can draw you a picture, the Earth is going around the sun because it has to go round and round in order to go forward in time. An object here has to go round and round to go down. For the Earth to go forward in time, it has to go round and round the sun, because that's the shape of the solar system, caused by the effect of the mass of the sun. So Einstein said, There is no force of gravity. There is no action at a distance. The sun curves space-time only where it is. That curvature spreads like the stretch on the bedsheet, and the Earth responds to that stretch only where it is. So there is no mechanism that directly links these two except for the curvature of space and time. And this is encapsulated in Einstein's equation, G equals 8 pi t. This is Einstein's greatest contribution to science. E equals mc squared is much more famous, but this is much more profound. This says the geometry of the universe is determined by the motion of mass and energy. So the common statement is mass and energy tells space and time how to curve, and space and time tells mass and energy how to move. It's a dance. Neither one leads. It's a completely mutual dance. They're leading each other. Space and time would not exist without mass and mass and energy cannot exist without space and time. In fact, they are really the same thing. So, now for a couple jokes. The story of Einstein's Nobel Prize. In 1921, the Nobel Prize Committee had a big fight as to who should get the Nobel Prize. Apparently, a lot of people didn't want to give it to Einstein, so they couldn't agree, and they put off the prize for 1 year. In 1922, they awarded the 1922 Nobel Prize to Niels Bohr, and the 1921 Nobel Prize to his good friend Albert Einstein. So it was a compromise. You give me one of yours, I'll give you one of mine. But when they called up Einstein, they said, "We want you to understand clearly that the prize is not for your work on relativity, which we consider far too speculative, and when you come to give your acceptance speech in Stockholm, you are not to mention relativity at all, because we just don't believe in it." Einstein said, "Thank you very much for the Nobel Prize, but I happen to be busy that day, so I won't be in Stockholm." This is like the President-elect of the United States saying, "I'm too busy to come to the inauguration, but, thanks for the election." Well, the King of Sweden was a little bit disturbed by all this, so he decided not to interfere in the Nobel Prize Committee, but rather to throw a state dinner with Einstein as the guest of honor, and he requested, "Einstein, would you please explain to us the theory of relativity?" Einstein was not busy that day. Time for another story. Okay, so the Swedish Academy rejected the greatest scientific discovery in 200 years, but they did give a Nobel Prize to a Swedish physicist named Gustav Dalén, who developed a device for controlling the lights and buoys. So obviously they know more than I do. Okay, another story. How about Einstein's two wives? This is Maleva Maric, Einstein's first wife, and Elsa. Maleva was Einstein's true love. She was the daughter of a Serbian general. She was Catholic. Einstein was Jewish. She was the only woman in the Polytechnic, or the college Einstein went to, and she was excellent in physics and math. She was better in math than Einstein, maybe as good in physics. And she had a slight hip deformity. Einstein's parents hated her because she was Catholic, Serbian, and had a hip deformity. She had a bit of a dark personality, and she was Einstein's intellectual peer. I'm not saying exactly the same, but in the same league. They enjoyed talking physics to each other. She aided him in the writing and research for his famous papers of his miracle year, and when they had nothing at all, they were madly in love, and everything was wonderful. When Einstein became famous, things changed. Let me skip over some stuff here. We're running out of time. All of a sudden, doors opened up for Einstein all across Europe. Some of them may not have been the most appropriate doors. And Einstein was not discreet about his infidelities. And I suffice it to say that he won his Nobel Prize for physics, not for fidelity. And this infuriated Maleva, of course, as you might imagine. She had given up her career to help him. She was busy at home raising his kids, and he was out gallivanting. So they became less and less civil, and eventually he demanded what was equivalent to an employment contract. She told him where to put it, and they were separated. Well, Einstein then started a romance with his first cousin twice over. They shared a mother, and their fathers were first cousins. So Elsa was an entirely different sort of woman. She was not an expert in physics and math. In fact, you can say she was no Einstein, except that her maiden name was Einstein. All she wanted was a famous husband to keep house and cook for, and that made her happy. That made Einstein happy. And she was willing to forget about whatever he did when he wasn't home, which made Einstein happy also. So Einstein pled with Maleva for a divorce because he wanted to go over to Elsa. And she said no numerous times, concerned mainly for the support of her children. And finally Einstein offered her half of his academic salary plus 100% of his Nobel Prize purse should he ever win the Nobel Prize, which he fully expected to do. Maleva, being the math whiz that she was, went off and did the calculation, decided that was enough money to support her kids for life, and she accepted. And Einstein promptly married Elsa. In 1922, when he got the Nobel Prize, she got $500,000, bought 3 apartment houses in Zurich, and managed to support herself and the kids for the rest of her life. So she got what she needed. Okay, so back to our hero. Einstein, this crazy guy that no one would hire, revolutionized our understanding of atoms, light, matter, gravity, motion, space, time, and the universe itself. Not too bad for a guy that no one wanted to hire. Thank you very much. I hope you all got one of my bookmarks. It's something for everyone, Democrats and Republicans. It has my website at the bottom. I do online radio shows. I have about 50 of these posted on my website. They're all free. Download them, listen to them whenever you want. So are there any questions? Sure.
You were talking earlier about how Einstein settled the debate between continuous matter and the atomic theory.
Right.
You know if Maxwell was an atomist?
I don't know if Maxwell was an atomist or not. Boltzmann was, and Mach wasn't. And those were the two principles that led the charge, for and against. Mach was a much better debater than Boltzmann was. Boltzmann turned out to be right, but he lost the debate. He committed suicide as a result. People sometimes take these things very seriously. Yes, sir?
I can't grasp the logic of the airplane, how it goes back first.
They see the same thing, the flip side of what we see, because velocity is relative. So it's impossible to tell who's actually moving. Okay? You think that you're not moving, I imagine. But actually you're moving east at the velocity of about 800 miles an hour because that's how fast the Earth turns. You're moving at 70,000 miles an hour around the sun because that's how fast the Earth orbits. You're moving at 500,000 miles an hour around the center of the galaxy because that's how fast the sun orbits the center of the galaxy. And at about 800,000 miles through the cosmic microwave background radiation, which fills the universe. So we don't really know how fast we're moving, right? So Einstein and physicists since Galileo have said that we cannot measure velocity except relative to something else. There is no absolute velocity. That's where the word relative comes from. You can measure it only relative. And all I we can say is that the jet and the Earth are moving relative to each other. We can't say which is moving. So whatever is true as we look at the jet has to also be true from the jet looking at the Earth, because they're equally valid frames of reference. Did I answer your question or just filibuster you? Okay, well, no one gets it the first time. Einstein didn't get it for 10 years, so don't feel bad. Any other? Yes, sir?
You mentioned we're about 5 years away from a good, useful fusion reactor. Can you go into that a little bit more?
Yeah, it's not exactly fusion, but it produces the same, it's called low energy neutron reactions. The key is you have a neutral particle instead of a charged particle that you're doing these nuclear reactions with. Charged particles, nuclei all have positive charges. They don't want to be forced together. But a neutron has no charge, so it's perfectly happy just floating into the nucleus with no resistance at all. So you don't need to have 200 million degrees, et cetera, et cetera. So the challenge is to make neutrons. If you can make neutrons, then you can do all the rest easily. And this is the process. You combine, in a clever way, protons and electrons on a surface of a conductor with a high frequency, high voltage field. Creates what Landau and Lipschitz call the plasmon. That will convert a certain amount of protons and electrons into a neutron, plus a neutrino. And then if you have an atom like lithium, that neutron can go in, blah, 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 and end up with 2 helium nuclei coming out. Step 1 costs you money, about 800,000 electron volts. Step 3 produces 27 million electron volts. And even after relativity, and even after quantum mechanics, 27 is still bigger than 0.8. This theory, the Windham-Larson theory, seems to me to be completely valid physical theory. They invoke no magic, no new particles, no new fields. They put together very well-established physical principles in a very creative way. I think it's 50% likely to work. The 50% includes the fact that someone's got to do some good engineering to make it happen. Yes, sir. At a company in Chicago called Lattice Energy. The only energy company in the world that's not funded by the United States government. This is not fusion, because fusion means nuclei coming together, but it's very similar to fusion, because you have nuclear particles going into a nucleus. So it's a bit of a semantics whether it's called fusion or not, but they don't call it fusion. And I don't know what you find on the internet. A lot of what you find on the internet. There was a famous fraud called cold fusion about 20 years ago. They probably did generate excess heat, and this is probably how they did it, but they didn't understand that. They made a terrible mistake when they called it fusion. Their process is absolutely not fusion. The rest of the physics community came down on them like a ton of bricks because they were claiming something that was obviously nonsense.
So this is not fusion?
This is not officially fusion, because the neutron is not a nucleus. I mean, it is a bit of a semantic hair splitting, but the important distinction is it has no charge. The problem with fusion is you've got 2 charged particles that don't want to come together. How are you going to make them come together? You can't do that at 300 Kelvin. Yes, sir?
Since this isn't actually fusion, have they named this process yet, or is that still something?
Low energy neutron reaction. Yes, sir.
How would this be introduced to the public? Would this be kind of like a long-lasting battery?
Well, that's probably the first application. What do you see here? This is hydrogen and this is lithium. This is a lithium hydride battery. It's no more complicated than a lithium hydride battery. The difference is you never replace it. It would last 100,000 times longer. They can also make this in the form of a power plant. It doesn't have to be lithium. It could be even gasoline. Lithium happens to be very nice because of the details of that process. Yes?
How did Einstein explain the Earth not moving any closer to the Sun in his general relativity theory?
Well, it's the same explanation as Newton, and that is that the Earth has angular momentum around the Sun. The Earth is not, if the Earth was stationary at any moment in time, the next thing that would happen would be it would fall straight into the Sun. But the Earth has never been completely stationary. The Earth has always been moving in some direction, and gravity pulls on it sideways and changes its direction. So it goes around in more or less a circle. Did I answer your question? If you think about the moon as an example, the moon moves forward every minute 38 miles in a straight line, whichever direction it's now pointing. At the same time, the moon falls toward Earth because of Earth pulling on it 16 feet. 16 feet isn't a lot compared to 38 miles, but if you add up those two vectors, it exactly puts the moon in a perfect orbit around the Earth. So those are the kinematics. Now, is it easy to do that? No, it's not. The particles that did not fall into the Sun are rare. 99.9% of all the mass of the solar system, as it began, fell into the Sun. The particles that didn't were the 1 in 1,000 that happened to have enough lateral velocity to avoid that. Yes, sir?
Can you explain us a little bit about the confirmation of Einstein theory on the eclipse of 1919?
Einstein, there were several predictions of general relativity, but the one that was most interesting was that light passing near the Sun would be bent by the gravity of the Sun. This is very different than Newton because light has no mass, so light shouldn't bend. And until Einstein, every physicist in the world would tell you that light would not bend as it passed next to the Sun. Okay, so Einstein predicted exactly the angle it would bend at. There was no variable parameter in Einstein's prediction. He had a certain specific number. If they measured anything else, Einstein was wrong. It was not that he could adjust something and fix it. It was either right or wrong. Okay, so how do you look at a star that's right next to the Sun? Well, we can't do that normally because the Sun's so bright. So the only time that you can do that is when there's an eclipse, a total solar eclipse. The moon gets in the way of the Sun, and we can see things that are very close to the Sun. And that happens rarely, and it happens in difficult places on Earth sometimes. And so in 1919, Sir Arthur Eddington made the enormous effort to launch an expedition to both sides of the South Atlantic Ocean, just off Africa and on the coast of Brazil, to photograph the total eclipse of the Sun. And he took all these pictures as the Sun was in totality, and he was able to determine, with some controversy, that the ray of light from a star had been bent by 1/2000th of a degree, 1,000 times less than the width of the moon. It was right at the edge of what was reasonable for instruments to do with the day. And he announced that result at the Royal Society of London, standing under an image that was 30 feet tall of Newton, England's hero for 2.5 centuries. And this was 1919, just after World War I, when you couldn't find 3 people in England who liked the Germans. And he stood under that image and he told the world that Newton's theory was wrong and this German guy, Einstein's theory, was right, and here was the picture to prove it. Then the newspaper reporter said to him, "Is it true, Sir Arthur Eddington," he wasn't sure yet, "that there are only 3 people in the world who understand Einstein's theory?" And Eddington hemmed and hawed, and finally the guy said, "Why are you waiting?" He said, "I'm trying to think of that 3rd guy."
Can we thank our
So again, thank our speaker again for the talk tonight.